Yes, Shubha.
Okay, one second. I might have to do this again. One sec. A little bit about me. Arnesh already mentioned I started my career in 1992, working for Square D in Chennai, but immediately took a break and then did my master's. And I've been in the Silicon Valley industry from 1996. I've been involved with SDN and the precursors of SDN from 2008. And I've worked directly with some of the key creators of SDN and some very well-known networking wizards. And I've also worked directly with the Cisco APIC team, who are the SDN vendors, well-known SDN vendors. Also worked with, on the QFX, which is a data center fabric from Juniper Networks. And currently I'm working on a new idea, but we won't go into that. So that sort of gives a little bit of a history of me with SDN. With that, we'll get started on the topic itself. So before we talk about software-defined networking, the first thing that we need to talk about are what are the components of the networking itself, right? So what is a network? How did it evolve? And how did we come about to the current state, right? Those are all the topics that we'll sort of talk about today. So first we start with talking about what does a networking device do? What does a router do? What does a switch do? So when you think of routers and switches, you should understand that each of these devices can connect through wires or wirelessly to create networks. Switches forward Ethernet frames and routers forward packets. And there's a lot of different protocol that are involved in the creation of this network and the packet forwarding that happens in the data plane. So I mentioned data plane. So when you talk about networking, you're always talking about different planes in which the functions are separated. So one is the data plane, the other one is a control plane, the third one is a management plane. So what is a data plane? Anything to do with the receiving of data, processing it, or forwarding that data, whether it's a frame, a packet, or a message, is all part of a data plane. So for example, if you think about how routers forward IP packets, if you look at the figure, host sends a packet to the default router, R1. R1 does some processing and then makes some forwarding decision and forwards the packet. Similarly, R3 and R4 also do the same thing. So any action that is taken per message in a networking device is said to be an action of the data plane. Is that clear? I just want to pause just to make sure I'm heard clearly. And if you have any questions, you can sort of either put it in the chat window. I'll address it if I can. If not, I could address it at the end of the presentation.
It's all clear, ma'am, till now. We could hear you properly.
Awesome. So, I don't have a clear picture of, where your level of understanding is with networking. So I'm just going with, a gut feel of what is expected of engineering students, right? So if it is too easy or too difficult, please let me know. I can change my, topic accordingly.
Yeah, sure, ma'am. It's like we know this, ma'am. We have started basic networking now. Till now.
Okay. Yeah, so, the data plane does the de-encapsulating, re-encapsulating packets, matching, the destination address to the address table, map it and find out how to basically route a particular packet from the source to the destination. It also does other interesting things like for network address translation, it changes the source of the IP destination address. And then if there are any ACL filters involved, it does all those processing as well. So all that is taken care of in the data plane. So when you come to a control plane, right? So we saw that the data plane uses a whole bunch of information, and these information are generally created and populated by the control plane and the protocols in the control plane. Some of the examples of these protocols are things like OSPF, BGP, ISIS, and so on. So, and the management plane is basically the ones that are the components that are used to manage the device, and the setting up the protocols and so on and so forth are all part of the management plane. So for example, in the traditional world before the SDN, things like Telnet and SSH and Netconf are all considered to be part of the management plane. So this is to do with a standard network, what are the various planes. Yeah. Was there a question?
No, I think someone accidentally unmuted themselves, ma'am.
Okay. So when we talk about this, network and the network planes, like you see in the last picture here, you can see that the data plane, the control plane, and the management plane are all in a single device. Okay, so that was the traditional network, where basically the data plane and the control plane are all distributed. In other words, each device has everything that constituted a network. So, and the other important thing to also understand is that each of these devices were vendor specific, meaning if you take Cisco or NetApp, each one had their own set of device, and they had a full control over how the data plane or the control plane or the management plane on their devices work. So that was all part of the network, the traditional network.
One thing, Shubha, in the control plane, you are having so many routing protocols, right?
Sorry, you're breaking up, Jams.
So you have a different type of a routing
Sorry, I
protocol.
call your professor.
Can you hear me? Can you of routing protocols? So can you just explain us like why you have a different routing protocols over here?
No, this is a traditional network only. So I'm not talking about anything new. I've not even started talking about software-defined networking yet. This is a network, typical network.
Okay.
And I'm just saying the control plane protocols are several. We have OSPF, we have ARP, we have BGP, we have STP. All those are different protocols that run on the control plane, right? Or they call the control plane protocols. That's all I meant.
Okay, so at the different
not,
point of a time, so many different type of protocols.
Not necessarily. Each of them play a different function. So the control plane has various functions, right? It has routing. So BGP is a border gateway protocol. So it's like it sort of says how the network behaves when it at the border gateway, right? OSPF is finding the shortest path to the next hop. So each control plane functions protocol offers a different function within the control plane. So depending on what is needed, a network administrator can configure a specific set of protocols on his network when he's designing a network. So that's what it means. Is that clear?
Okay, fine.
So we are still, I think for a while I'll talk about traditional networks, and then only we'll switch into SDN to give. I'm not going into the very technical details of SDN, but more an overview of what is SDN and how it's coming about, right? So it's about why we got into the SDN conversation at all, right? So that's what we will address mostly. Yeah?
Yes. Go ahead.
So that brings us, once now we understand the control plane, the data plane, and the management plane in a traditional network, we should also talk about how were these networks architected in a data center, right? So now to talk about that, we have to understand what a data center is, right? So data center is where, like, in an enterprise, right? I worked in a HP. So when you work in a company like HP, all the internal applications are run off of a data center, meaning all the servers running the applications are connected to a backbone of network, and all the necessary application for safeguarding those stayed within this data center, and there were edge gateways that sort of connected to the public internet from there. So that's a data center, for example, right? And there were different specific architecture that were used in many of these enterprises for their network connectivity. So we'll talk about the first type of architecture. So this was a traditional data center 3-tier network architecture. There were 3 kinds of switches, right? The one in the bottom, the one with the arrows in the bottom, they are called the leaf switches. And on the top of that, there was a layer called the aggregation switches. And the top layer was the core switches. And what is not shown here in the picture is the connection from the core pictures here to the edge gateway that connects to the public internet, or things such as firewalls and maybe load balancers, or a whole bunch of other edge functions, all operated outside of this architecture, right? So, but this is the main architecture that served the applications within the data center, and connection to outside the data center, right? So when you talk about this architecture, there are a few key things that we need to understand. So the second layer of switch is called the aggregation switch, and the core switches on the top were all very expensive chassis-based switches with multiple line cards. I don't know if you sort of know this, like, when I was in Juniper, so that was one of the key projects that I was part of, which is basically how do you take the chassis based switches and make it the best in the industry, right? What protocols do we need to run? How do you add capacity? How do you make sure it's fault tolerant? How do you make sure the service level agreements are all maintained, and so on and so forth, right? So those were the key projects that companies like Juniper and Cisco, NetApp, all those worked in the late 2000s. So that was these were all giving the foundations to SDN, right? So this particular architecture was brought up in mind with basically to give predictability for the traffic flow between the users on the north, or on the that's connected to the core switches and through the public internet, right? That's called the north, and the south is in the bottom, which is basically the applications are running on hosts and that are connected to the access switches. So the traffic flow that flows vertically through this network was called north to south. So this particular architecture was optimized for that specific traffic. And one more consideration when you're talking about this specific architecture is this, since the aggregation switch and the core switches were very expensive, they were heavily oversubscribed, meaning if all the hosts or the servers that were running or that were connected to the access switch were to actually send traffic simultaneously at full rate, the performance will really be bad because of the oversubscription on the aggregation and the core switches. So those were some of the ways in which this particular architecture worked. And so when you talk about this architecture, we should sort of consider all the drawbacks of this architecture and why we came into the next evolution of the network architecture in a data center, right? So these were some of the issues with the 3-tier architecture. So there was a difficulty in scaling up to meet the high demand of the application, right? So let me tell you what that means. So if you add maybe tens of devices to handle an application that is going to be added with high performance needs. So what happened was you have to change the network topology. You have to rewire the connections to the aggregation switch, and you have to figure out how it connects back to the core switches, and make sure the traffic flow on the north-south traffic is maintained. So there are a lot of work from a network administrator when a particular application needs are increased, and new devices need to be added. Also, another issue with this was, since that particular the three-tier architecture was optimized for north-south, what happened was the traffic flow within the network sometimes will have to actually, within the data center itself, we have to go all the way to the core switch and be back, which means that the latency was unpredictable. Sometimes it is a direct hop through the top of rack switch or the access switch to the application very quickly, or sometimes it goes up all the way to the core switch and back. So the east-west traffic flow was variable, and variability was never a consideration. Is considered a negative thing when it comes to application performance. You want predictability and not variability. So that architecture did not work for east-west traffic performance. So, and also another thing is the network architecture was pretty static, right? Even though the server virtualization and containerization, all those gave to a more dynamic environment. So the applications were not monolithic. So in the early days, right, when you set up an application, the application ran on a particular server and it stayed there for its lifetime. In case of even high scalability, when I was part of Tandem Computers, which was known for high scalability. In that case, the way capacity was handled was when you basically give the server, hey, you can have 10 instances of the server and you can run on machines A to A, B, and C, not more than that. So that's how you configure for scaling. So you may start out with the servers running just on A, but eventually you'll add B and C. But this is all defined statically in the configuration. But dynamically, the instances may come up within the configuration that has already been set. However, with server virtualization, everything changed. Everything was dynamic, right? Application with things like vMotion and other things that was introduced by VMware with server virtualization, a workload can move from part A of a network to part B. And so it was very, very difficult for network administrator to manage and configure and control the policies within the network in such a case. So that left to non-compliance. If there was government networks, you cannot really sell to the government because it wouldn't pass all the regulatory concerns, right? And was pretty vulnerable to security breaches because one part of the network would be secure while the other devices that were newly added might not have the same policies enforced. um, you know so they were it was very cumbersome and difficult for architecture with the scale of the scale demands increased, right? And also, as we talked about, right?
No,
So
how do you mean, what do you mean by that, Shubha? That is, you are telling that there is a vulnerability breach. One part is, when one part is given, the other part is not able to get it. How do you say that?
So meaning, you might have secured part of the network with certain set of policies that allowed for that particular set of applications to be very secure. Whereas there might be some parts, since you don't have a consistent network policy that can be applied across all network devices uniformly, you might leave out one or two, which may give you a backdoor entrance into the network and allow you to get inside the network and do things with other applications that you shouldn't be. And in terms of like multi-tenancy, you might get, accidental access. You might give accidental access to things that are not belonging to your tenant, right? But somebody else's data, because it's a data center. So all those kind of possibilities were there in a traditional network. It's not like it's not impossible to control it. It was just cumbersome because the network administrators had to be top of all of these things. So with the server virtualization and the loads randomly going from one location to the other location, and the addition or of devices, all made these vulnerabilities even more higher risk. Is that clear?
Okay. So you mean to say that because of the integrating many devices, that problem is there, and different companies are working on different set of policies. So that problem, due to that problem, so it will not be activated on
Oh, no. So when I
all the
say
devices.
so now, no. So when I say policy, it is policy within the network, within the data center, right? So if you want to say, hey, I want this specific quality of service for this application, I want this quality of service for this application, I want these paths secured for this application, these paths secured for another application B, those are policies, right? What are the ACLs with this application? What are all the ACLs of another application? These are all general policies that govern a network, right?
Okay.
And
Okay.
we're talking about a network within an enterprise. I'm not talking about the public internet. Yeah, that's not what we are talking about.
No, I
These
mean
are
to say
enterprise
that
networks.
across enterprises, there will be variations.
Of course, right? Even within an application, each application's need might be different, and hence the network requirement might be different for each of these things. So like, if you take a real-time video processing application, its need is very different from a bank's transactional data requirement, right? And the policy and the securities are very different between these applications. Both these applications can be hosted in a single data center on a single network, right?
Okay.
So the application itself had the intelligence or the understanding of what it's needed, what it needs out of a network. However, this particular architecture did not give that flexibility for the application to program the network for its own needs, right? Because there were general policies that were applied from device to device. Each device might have a separate kind of policy enforced because it wasn't totally automated, right? It was usually automated through scripts. But you might have a single script that says, hey, apply this policy across devices A to A, B, C, and D, and that was all the automation there was. There wasn't a way where, yeah, as you configure an application, the application itself sort of tells the network or what to do, right? What is the traffic expectation for me as an application? So those
Okay.
things were not there, right? Those were all the drawbacks of that network. So as we come into modern ways in which data was used, see, in those days, we were only talking about, I remember I had, in HP, when I was there, a server connection of 4096 server connection was considered humongous, right? It's so tiny in these days, when you're talking about a connection to a server or, a particular device. So the scales have increased tremendously, and so the needs, right? So
Okay.
that's what I meant by the three-tier architecture, and that too was the specific way in which the aggregation and the core switches did not do well for the virtualized environment, which is pretty much in vogue today everywhere, right? Everything is a VM. We all talk about VMs, but
Okay.
VM introduced a whole shift in the network paradigm. So that actually gave rise to the next architecture that we will talk about. Okay.
Okay.
So we went from a two-tier architecture to a three-tier architecture to a two-tier architecture. So what this two-tier architecture did was it made sure there is only a single hop between the access switches, right? Which means that, so let me, so the east-west traffic is the traffic that happens within a data center, right? So that's called east-west. So when there is a traffic flow from the last boxes here, the last set of boxes in the picture, that's called east-west. If the communication between that goes horizontally between this layer is called the east-west traffic, right? And also in this particular architecture, the way it was done is you can add a device, you can add an access switch pretty easily, right? And because it's a full mesh architecture, the way the full mesh was much easier to implement by providing this Tor switch, right? So this particular way in which it got connected was called a CLOS fabric. So there was this person called Charles Claus. CLOS is how I remember all the Juniper folks saying it, so I say CLOS, but that must be a name. It's a name, and so it must be Claus, right? So Charles Claus was the one that actually theoretically drew a performance model for a fully meshed interconnection. And since it was a fully interconnected, mesh, it was called the CLOS fabric, right? So in this model, there were two advantages. You sort of removed one layer, an expensive chassis-based layer, right? And you just have the access switches, and finally the spine switches, which is the backbone. So it was pretty much like a chassis. The spine was the back end, and the access switch or the top of rack switches were the line cards. And another important thing is, you know, so basically this flattened the more traditional architecture, right? And um, each of these access switches were actually connected to two spine switches. And so effectively it was a large chassis based switch, right? And then the east-west data flows in this architecture takes the same number of hops, irrespective of whether the destination was right next to itself or further away within the network. And it can be load balanced, and it was also loop free. So one of the biggest difficulties in that the network had was it had to solve the problem of redundancy and had to provide multiple paths to the um, from a source to a destination. However, that caused loops, and they had to come up with various ways to prevent loops. And when you Google the topic, loop detection in networks, you can find millions of articles on that, right? So it's a very
Okay.
well-known problem, and it solved. The three-tier network solved it with STP, but STP was performance intensive, right? Meaning, if you want a real-time performance on a network, and if STP is involved, you can forget it, right? It'll be awful. So this leaf spine architecture also removed STP, and and the latency information, latency was much better in this. So, and this architecture, along with the concept of SDN, was becoming the norm, right?
அந்த கிளாஸ் ஜாயின் பண்ணிருக்கியா?
Yeah. Question?
Somebody accidentally unmuted themselves. You can continue.
Okay. Sorry. Okay. So basically, even here, when you talk about the next, the drawbacks of this, what did it solve from the three-tier network? So it definitely solved the east-west traffic performance problem.
Shubha, we are unable to hear from you. Are you there?
Hello, can you guys hear me?
Now, okay.
Did I lose you guys somewhere in between?
Yeah, now no presentation. We couldn't see the
Yeah,
presentation.
so give me,
Yes.
yeah, let me share the screen again. Okay, let me go to a different room. I think that might hopefully help. Just give me 1 sec. Yeah, is it better now?
Yes.
Yeah. So I was talking about the drawbacks. Oh, actually, I have a typo here. This is the drawback of the two-tier network, right? So basically it's the same slide as
Yes,
the
yes, okay.
three-tier network, but what the difference is, the two-tier network improved the performance of the east-west traffic. So that drawback was gone. However, the rest of the drawbacks still remained in a two-tier network, right? It was still the same difficulty with, when you scale up, you can add a device. However, adding a device as a singleton is still a problem. It was without a more centralized network management, the same issues as a three-tier architecture remained, right? So this gives us a transition to SDN. Basically, as as this network came into being in many enterprises, and as the difficulty of the configuration still remain, however, performance qualities improved generally about the network, people started thinking about the problem of the management of the network as a whole and started to question, right? So that brings us to the SDN roots, right? Where did it begin? So when you talk about the start of the evolution of the SDN, so each of these networking companies were working on figuring out how to optimize this network. First, they optimize the east-west performance, and the north-south was already optimized in the initial network, and the east-west performance or improved. However, they still had this problem of vendor-owned devices, right? And there was no abstraction. So we'll come to all of those, right? So there were some projects, well-known projects.
What do you mean by here abstraction?
Abstraction is we will talk about at length in the next few slides. Just
Okay.
hold on to that thought, right?
Okay. Okay.
So basically, when you talk, I do have a slide on that topic.
Okay.
So
Okay.
the beginning of the SDN started with trying to figure out if we can separate the control plane and the data plane, right? And there was this project called Epsilon. It's a well-known project. Again, Google search it, you will know more about it. And that there were some early efforts on that. And there were companies like, Aruba Networks, Meraki. All these networks were networking companies were focused on how to do the management of a wireless network, right? Simultaneously, companies like HP, Amazon, Google, all of them were working on how to control the data center networks. So that was some work there. So I mentioned about HP's project, right? And so when I was part of HP, one of the projects that I was involved in is called was the NeoView project. So this was before 2008, right? So it was somewhere in the 2005 to 2008 timeline. So that timeline, the project was basically, I think the customer was Walmart. Walmart had about 30 data centers, right? And 30 data centers were to be managed was really, really difficult. So basically, the company wanted to bring the 30 data centers down to 6 to 8 data centers. So the HP NeoView project was that. So I was part of the tandem nonstop computing division, and it was known for its high availability and high scalability and fault tolerance. And we pretty much rewrote the whole stack to allow for optimizing the data center. We can't go into that detail, but just to give you a history of the number of years the precursors of SDN was bringing us to this point, right?
Okay.
And
so basically, they are trying to optimize the data center, and that was a major root cause for bringing in a lot of changes.
yeah, so basically, every enterprise understood that the network is not functioning as well as it should. It wasn't, so the rest of the world was moving so fast, but the networking was pretty much stuck in its same place for a long time, right? So
Okay.
the application, applications were improved tremendously, and all the various layers when you talk about a stack of in the internet, every area of technology was improving, but networking was pretty much the same data plane and the control plane for years, right? But there were precursors. They didn't touch networking per se, but the concept was to simplify the data center and make the management and configuration of the application all the way from the bits to the actual sophisticated user end applications, right? So
Okay.
both spectrum to be optimized for easier management and total cost of ownership, right? So that was a big enterprise. When you take an enterprise, when you go into program reviews and enterprises, the main thing that we typically talk about is capex and opex. What does that is? When you're what is the total cost of ownership of anything that you have, right? All your capital equipment, right? So that's how a network was measured, right? So
So the
those were all
capital
factors.
equipment, the capital resource reduction also they expected.
So everything, right? So
Okay.
when you basically have an automatic way of knowing what is going on a device, how much capacity is there, how much underutilization or overutilization is happening, and if you're able to automatically provision more if there is less, and less when it is less, if we can put more application on top of that device, then you optimize on the capital, right? So bottom line is to be able to control the network in a very programmatic and automatic and intelligent way. So that was the requirement, and that is the precursor route. Is that
Okay.
making things clear?
Yes, yes. So, first point, what I understood is that so basically they were looking for the optimization and resource utilize, that is the number of, that is ownership of the resources should be very less, and they wanted to have a control, and the controller automation they were expecting.
Yeah. So yeah, we will talk about that the specific gains with SDN at a later point. But these were the holes
Okay.
in the architecture so far, right? And many
Okay.
people were working on it. It wasn't a single idea. But in 2008, the founder or with the team, the Nicira team, which were initially part of Stanford, was working on this something called a network operating system and OpenFlow. Okay, so that was where the actual cohesive definition and beginnings of SDN happened. Okay,
Okay.
so sort of reiterating, what we were uh, talking about is the why and the what, right? Why
Okay.
was SDN needed? It was hard to manage, networks are hard to evolve, and the network design itself was not based on any kind of formal principles. What do you mean by that? So, remember these were the times of Java coming into being, right? Object oriented programming, abstraction, modularity, containerization, all these containerization came in later, but all these modularity conversation was happening in the same time, right? So everyone on every part of the technology were talking about how do we build a system that works well. So for that, the system needs to be created in a tractable component. What does that mean? Easy to create, easy to manage, easy to independently evolve. That's what means tractable components. So that's a good system, right? So if you can't manage, evolve, or understand a system, then you probably don't have the right abstraction. What does that mean? We'll talk about it in a second, right? So the little bubble, which I think should come. Okay, so this person called Barbara Liskov sort of was created this principle called the substitution principle. So this is the basic of Java, right? Um, Basically, it's saying the superclasses should be able to use all the methods of the subclasses, right? That
Okay.
is the concept of abstraction, right? She made this famous quote saying modularity based on abstraction is the only way to get things done, right? So that was the thinking in the rest of the industry. And that was coming slowly into the networking world, right? So
Okay.
the question came about what are the abstractions that we need, right? We talked about the network, we talked about the planes, we talked about the 3-tier network, we talked about the 2-tier network, and we understand what the problems of the network are. Now we need to talk about what is the abstraction that we are talking about. What is abstraction, right? For this, we need to understand again what was the state of this networking before the SDN, right? We knew that data plane did a certain function, it forwarded packets, and the control plane controlled how the data has to flow, right? And they solved very different problems and needed very different abstraction. When you talk about data plane, everyone remembers their OSI layer, right? Can someone say the few OSI layers for me here?
Yes,
Anyone?
students.
Application layer, transport layer, a network layer,
Physical layer.
before that data layer, data link layer.
Excellent. So, OSI layer also went from the 7-layer protocol to the 4 layers. We won't talk about that. But what it says is all of those 7 layers were pretty much, we would consider that as the packet flow, right? So in this, what happened is the application was built on a reliable transport and then packet delivery and then on the transfer of the bits, right? So every layer, the layer that did the transfer of the bits evolved independently of the layer that did the local delivery, like the Ethernet, right? And then independently is the transport layer, the UDP and the TCP. Each of those layers had specific interface to the layer below and above, right? And each of them evolved independently. So that's an abstraction. So the data plane was built on a set of abstraction. However, the control plane didn't have any such thing, right? We talked about what does the control plane do. The control plane had a lot of routing protocols, and each of those routing protocols has its own set of goals and what it needs to accomplish. So it wasn't layered by any means, right?
I have a
So
doubt. I have a doubt, Shubha. That is, you were
yeah,
telling that data plane and the control plane solved very different problems and require different abstraction. But you are saying in the third statement, control plane has no abstraction. Can you just put in a thought, like what make you to write that first statement and to the third statement?
no, the control plane solves a different problem and require abstraction. It didn't have an abstraction. What we are saying is it needs an abstraction, right? That was what was missing, that didn't allow the programmatic approach to control a network, because the control plane was not programmable, right? There was no
Okay.
abstraction saying, you know uh, there was no standardized way in which the protocols worked from network to network, right? Everything had to be hand managed. Is that clear?
Okay.
So it didn't have an abstraction. And the SDN provided a way of abstracting, right? We will come to that. What exactly it abstracted and made it more standardized and made the interfaces standard so that the control plane can evolve, right? The data plane evolved, right, into these very clear-cut OSI layers that sort of define how the packet flows, right? And
Okay.
that was the reason why our internet was a big success, right? When you talk
Hmm.
about this, when you, what did the internet do? It went from, like, maybe megabytes of data in the 1999s to hundreds of petabytes. I don't even know the number of zeros behind the bytes count at this point of time, right? It's
Okay.
hundreds of and thousands of petabytes of data per second. That's how much data we move these days, right?
Okay.
But
Okay.
the same abstraction of the data plane survived. Why? Because we didn't try to solve all the networking problems at a time, right? Each component evolved independently, but they worked well together. So that was the reason for its success. So the founders of the SDN basically wanted these successes to come across all layers of the managing the network, right? Which is the control plane, basically. So given that we know how the data plane worked, so we need to figure out how can we improve the control plane, right?
So they are
So
bringing
that
in
is the
that
key part.
internet concept of dividing that layers into control plane.
Yes, exactly. So the internet success was basically because of the way the packets are routed in layers, right? And
Okay.
that's all. So that abstraction helped. But if we can sort of bring a similar kind of a construct, not exactly the same, but just the general idea of abstraction and separation of concerns. So the data plane can do what the data plane needs to do. The control plane does what it needs to do. The management plane does what it needs to do, independent of each other. They just need to have a clear understanding of the language they talk to each other. Otherwise, they should be able to grow independently. So that was the goal, right? So what was the first thing that happened was, how do I identify the reusable components, right, in the control plane? To do that, what does the control plane need to know first? So it needs to tell the network devices what to do, right? But for that, it needs to understand how does a network look like, meaning the topology of a network, right? And it also needs to understand how to accomplish a specific goal on a given topology. So if you draw a map of the network, which is what is the topology, right? And if it wants to do a specific goal, like apply a specific QoS or a SLA to a bunch of devices in the network, so that's like specifying a specific goal. So that may vary from application to application. So that's not something that we could actually create a reusable component. Telling the switches what to do, pretty much all the control plane protocols need to tell the switches what to do. So what the SDN founders did, they said, okay, let's build this the controlling program, or the control plane for the SDN by determining just the topology information and also configuring the forwarding state on the network device. They found these two as the key components that needs to be reused. That's pretty much as SDN. That's the simplified version of what SDN does. Do you understand why we talked about this so far?
Yeah.
So
I think quickly
what
you have
is
to go. You have less
yeah,
time already. We are 10.
yes. So couple more minutes, right? So what does the SDN do is, like, it gets a global network view, and it also defines a forwarding model. So the global network view is implemented with the network operating system, right? But network operating system is also just software that runs on the servers in the network. But this software can directly talk to the switches through this forwarding model, right? Forwarding model is nothing but a standardized way of communicating with communicating the forwarding state to the network device. Okay, so
Okay.
so that brings us to the industry-wide definition of SDN. So I won't spend too much time on this. If you look up SDN, each one comes up with a different way of defining SDN. I have a few sampling of what it is defined. So in essence, this is a paradigm where we could modify the behavior of a network devices, right? In a very programmable fashion. So that is the insights. If we can find the topology of the network automatically, and if you're able to tell the switches automatically how to modify the forwarding state dynamically and programmatically, that's SDN. So that brings us to the three layers of the SDN. So the infrastructure is where the network device or the devices are, and the control layer is where the brains of the network resided. There's three components: the control program, the network operating system, and also the routing protocols and so on and so forth, right? So it's also sometimes called an SDN application. We won't talk about that in too much detail. So the network operating system did an independent job. What is its job? Was to understand how the network looked like. But what does a control program? So the control program, what it does is understand this topology and decides what needs to be done. Basically, it is whatever the operator wants to do, the control program will do it for the operator. Like if the network administrator, right? So the network administrator comes and says, hey, apply this particular policy on this set of devices in a dynamic fashion. So basically the control program will basically do that, right? It will communicate to the switches and tell them what to do. So that was the job of the control program. The network operating system does nothing other than talking to the switches and getting to understand what is the topology, and and any configuration changes, it'll send it back to the switches. The switches are pretty dumb devices that just follows orders, right? That's pretty much the SDN architecture and the ways in which SDN is defined. So the key component of the SDN is the controller, right? It gives the centralized view, and also is used to dictate the policies across the network. And because it can be done in a from a single pane of glass, the manageability of the network becomes really, really, really simple, right? So
Okay.
we quickly come to the advantages. Again, it's virtualization, orchestration, programmability, dynamic scaling, visibility, so on and so forth. So before I close, just wanted to say, I worked with both Cisco and VMware on SDN, but very, very, very different ways in which SDN was approached. If anyone interested in this topic can read up further on the Cisco EPIC, which did basically SDN through intelligent hardware. And VMware was a complete software overlay without consideration of the underlying network. You can have any kind of network. The overlay will take care of the virtualization part. So with that, I think I will wrap up. If you have any questions, feel free to shoot it to me through your prof. Yeah.
Students, why don't you switch on your video, students? Let me see who are the participants. I don't have my camera today, unfortunately. Yes, those who are attending. Yeah, 3 people, committee people are here. Yes, others? Just open up and let me see.
In software engineering from Anna University in 2002. She worked as a research scholar under the supervision of Dr. Chitra Mam, professor and head of department of CSE SSN, and received her PhD in software engineering from Anna University in the year 2013. She has organized the international conference IEEE ICC IDS 2019 and reviewed many conference papers and journals. Also, Ma'am is one of the editors of the book IGI Global. She has been organizing many workshops, competitions, project colloquium, and seminar to the students and research scholars and faculty members under the banner of SSN CSI Students Chapter. She presents to us today deep insights into network security using Mininet. Over to you,
Yeah.
ma'am.
Yeah, thank you, Joshua. And what the participants, why, I think how many of them are registered?
About 35, ma'am. 35 to 40 of them.
35. Okay. I find the very less 10th. Okay. And those who are here, why don't you switch on your videos? Let me see who are here to the Mininet environment. So Mininet environment supports SDN. Okay.